Howdy and welcome to my channel. In this video I'd like to do a review of the UEI DM397, which is a true RMS digital multimeter. Has a 1000 volt Cat3 rated, has a data logging kit that is included with software. It has two displays. It has a 50,000 count and a secondary display that's 5,000 count. One interesting thing that I haven't seen in some meters, it can test your leads and the internal fuses. It has a min, max, and average recording capability. You can also store up to 20 readings in the meter without having to download them to your PC. Resistance scale goes down to a 1,000th of an ohm resolution. Has a temperature probe included, a K-type. It has capacitance, frequency, also duty cycle with pulse width measurements. Has a 1 millisecond peak capture capability. It has a DBM and a DBV for testing. And has your fuses and battery are available once you remove the access cover on the back. And talk a little bit about that, taking the cover off shortly. You might notice up here at the top there is a slight line across there. That's simply a reflection with my lights and everything, so the overall display is reasonably not too bad in terms of reflectivity. The color tends to sort of match some of the flute colors, so kind of a yellow there. And take a look at some of the accessories. The UEI DM397 company is located, I believe, in Beaverton, Oregon, in the United States. And I think it was assembled, put together in Taiwan. When I checked today for pricing, I think the retail price is around $293. I've seen several companies that offer it on sale for about $235. I got a special purchase over the Christmas holidays at about $215. And I do also believe that this is their sort of flagship multimeter. What you get in the box is a couple of probes right here, and you get some software for your data acquisition and everything, and possibly the PDF file for the manuals available on here. It is also available online, which I downloaded and I like to print it out. It's a larger format. You get your optical connector to go to your computer for data logging. You get a K-type thermocouple. And also included for the clips, you get some, they're threaded, so they're screw-on alligator clips to the probes. And we'll take a look at each one of these a little more individually. It's an integrated rubber housing or cover on the outside, bail in the back, single access screw to get into the batteries and the fuses. Again, it's molded all the way across here. I'm sure you can't remove it. As mentioned by another reviewer, this down area on the lower models is actually, the lettering's engraved into the rubber right here. So that's probably a good thing, so it won't rub off too easily. Plastics seem to be good. Rubberized buttons seem to be nice. Again, relatively large display, sort of old school green color, but the characters are pretty crisp. We'll take a look at that. Rotary switch for your different functions that go across. Your optical off the top would be kind of nice. These are exposed. It looks like there might be two unless one is a filler, so I don't know if it's bidirectional or not. We'll check that out a little bit later. But it'd be nice if maybe there's a rubber cap that would go over this, kind of protect them a little bit. If you twist or try to bend the unit, it's very solid. It doesn't flex at all really, so that looks really good. Even though when I was showing the bail, it's kind of looks light duty. Again, this is an anti-static mat, so it doesn't slide around at all. It's easy to turn the unit on and off. And if you put it on a slipperier surface, smoother surface, I found it to be pretty stable. So not bad at all. Taking a closer look at the probes that come with it, they have some caps on the end, which is kind of nice. They are sharp, and therefore it's kind of helpful that you don't take your blood type or something with them if you're reaching around in a bag or something to get them out. So these both come off. And they're a little on the small side. Again, this is sort of their flagship. I noticed you can purchase these as an accessory from some vendors for around $10, so reasonably inexpensive. But again, somewhat short. There's some lettering on here that's raised, so the tactile feel is not the best, I don't think. Don't particularly like that. And the strain relief on here is really just a continuation of this plastic, which I think is really poor. So it doesn't flex at all. It just has a nice pattern in there, and usually some of these are somewhat rubberized or something, so you get a little bit better flexibility on the strain relief. So I don't really see how this is any better. So I think that's pretty poor. This is my second DMM video, and I don't really plan to do a lot of DMMs. The reason I'm doing this second one is basically I've purchased a couple of the True RMS meters, and so that's why I'd like to show it. There are some people that do a lot of reviews. Martin, and I'll put his link in the show notes below, has quite a few reviews on digital multimeters, and be a good site to check out. As well as Dave, I'll put his link also in the bottom, and he does reviews and compares a lot of different ones. Again, since I'm a hobbyist and I have to purchase all these, can't really afford to get a hold of a whole bunch of different ones for comparison. So I'm planning probably in future videos to do some other examples. You know, I've been requested maybe a troubleshooting review, so I might try to do one of those. In fact, it might be nice to use this meter in that because of the dual display, and sort of talk about some of the advantages of that. Taking a closer look at the front panel of the DMM, we have 4 soft buttons. We have a range switch, min, max, and average, a 1 millisecond peak, a rel, a delta. We have hold and auto hold. We have our memory, and we have a backlight off the memory button. And then on our rotary switch, we have AC/DC millivolts, AC/DC volts, hertz with duty cycle, ohms, continuity check, capacitance, diode testing, and LEDs, your temperature. You have a AC and a DC microamp, and you have AC/DC milliamp and AC/DC amp. And then 4 banana jacks for most of your common things through here on your volts, ohms, continuity, diode, temperature. This is your common connection right here. Again, as I mentioned earlier, it's Cat 3 rated, 1000 volts. On this side, you have your milliamp, microamp input and fused, and you have your 10 amp range, and they say again, a lot of manuals, 20 or 30 seconds, you can do up to 20 amps before you start smelling plastic burning. Okay, taking a look at the display, we can turn the unit on down here, and of course everything shows up for a couple seconds. It indicated it was a backlight, which is off to the side here, and we'll show that in a little bit. And again, you can see it's sort of it's a green display. The characters look pretty clean and everything, and not too bad on the reflections. And this, of course, is your enunciator for your soft keys. And I'm going to be honest with you, it took me a couple minutes because I kept looking at the enunciator saying, oh, it's AC, but it's actually DC with the smaller lettering up here. And so I'm kind of embarrassed, but 1 or 2 minutes I kept going, pushing the wrong buttons. But it does make a lot of sense. There's quite a few enunciators down in this low area, that's why it's a large field, and they change as a function of your rotary selection switch. And we're on the millivolts, and notice when it powered up, it comes up into DC. So it measures DC millivolts, and we have our decimal point right here. And so you can see we have millivolts, and there's 100 microvolts, tens of microvolts. So you get down to least significant digit of 10 microvolts. So reasonably good resolution. Again, as I indicated earlier, it's a 50,000 count meter. Okay, and then to go from DC to AC, you simply just press the soft button right here, and then you can see it goes to AC, and again the enunciator appears telling you what the display is doing. And now the soft button over here is if you want to return to DC. And it just takes a minute or two to get used to that, and it's pretty nice. I actually like it after I kind of adjusted to it. And because it's a dual display, which is kind of a nice convenient thing, you get your frequency for the AC as well as the AC measurement. And again, we're on the millivolt, 500 millivolt scale. And here again you can see that this is our 50,000 count display, and this is our 5,000 count display. These two update about 4 times a second nominally. And there is a bar graph. It's a 25 segment bar graph. It updates approximately 40 times a second. To see the operation of this, we're going to again use the DMM Plus calibrator. Again, not laboratory quality possibly, but still pretty nice, especially for hobbyists. And so I'll be using it, connecting up the leads to it, and just kind of run through some of the different modes of operations of the meter. Again, in these measurements, I'm going to be using the Fluke test leads, kind of partial to them. And we'll turn on the calibrator, and we're going to go to DC, so just press DC. And we're on the 500 millivolt range. This is putting out a higher voltage, so we're getting our overflow indication. That's what it looks like. And so we'll flip the rotary switch up. By the way, the switch feels very good. Nice contacts, good snap action. One thing I don't like about it, if you notice, you can hear it beep. I do not believe you can turn that beeping off, and I find it a bit annoying. There's plenty of tactile feedback of this switch snapping, even the click. You can hear the click is very solid. I don't know why you have to have this thing beep. So that's a bit of a disappointment. So we'll go over to DC. And the value on this calibrator is supposed to be 5.0000 volts. We are at a slightly lower temperature in the lab. It's the early morning, so not at the 70 Fahrenheit spec. And we could compute the difference of it again just to get a rough idea. It's not toggling around too much either, so it looks really nice. And it's just slightly below its 5-volt range. I can zoom in really close so you can see over in this area, which I do like. You can. Puts an annunciator up there telling you the range that you're on. I find that kind of handy so that you can quickly see the range that you're on, even though we're in auto ranging. And then as you use the range button to cycle through, makes it nice and convenient. Okay, switching the thing over to AC is very simple. Simply press the soft button here for AC. Then I'll change on the calibrator to AC. The AC reference voltage is supposed to be 4.999 volts, and we're reading 5.008 volts. Another thing that's convenient on the dual display, as you can see, we're reading the frequency up there at 99.9 hertz, and according to the testing thing, it is 99.9 hertz. Okay, again, another thing that's kind of interesting is when you first turn it on, it goes into DC on the millivolt range, but then when you switch from millivolts to volts, it goes onto the AC range, and I would prefer that it would stay on the DC. So as you can see back here, when we click it back, we're on the DC range up here, and then when we flip it over, you can see it changes over to the AC range. And I would like it to be either programmable or that it would stay with one or the other. And of course, again, my interests are in the electronics area, and so I'd prefer to have it default to DC. The next position of the rotary switch is the hertz. So we go over there and take a look at it. Okay, in this test, just going to check out the frequency response. They say the counting of the meter can go up to 5 megahertz if you put in at least 250 millivolts RMS signal. And I'm going to do a sine wave on this, and we're right now at just 60 hertz, line frequency for my particular area. I'm using a coaxial cable, and it's important to match the color of the cable to the meter. It probably makes it work a little bit better, I think. And it's a 50 ohm output impedance, and since we're going to go to 5 megs, rather than putting the terminator here, feed through 50 ohm terminator here, should put it at the end of the cable to minimize reflections. Hope to reduce down the any VSWR problems. This is good to 500 megahertz, 1.12 VSWR. So what I'm going to do is I'll connect this on, so it's basically a 50 ohm load. Connect it in, and then you have your ground ridge right here. I want to make sure you can do that. So I'm going to put the ground into the common of the meter, and we're setting up again at 60 hertz. Wavelength is maybe 3,000 miles, not a big deal. Probably, and you can see it's reading pretty good. This instrument's saying it's putting out 60 hertz, and meter's reading 59.99 hertz. And so what we can do is we can select the frequency here, and let's just hop right up to the 5 megahertz. And I've already set it at 250 millivolts, so push the 5 in here, choose megahertz, let it do its ranging, and we're at 5 megahertz, and it's reading 4.9999 megahertz. So it looks like definitely within spec, and sensitivity seems to be okay too if you're down at the 250 millivolts where they spec'd it out up to the 5 meg. Just for grins, maybe go to 6 megs just to see if there's any difference. There's 6 megs right there. And no, it jumped up a whole meg, and now of course we're dropped off. So at least they are within spec, and we could find out exactly where it started losing it. But definitely useful up to that frequency. Also supposed to go down to about 0.5 hertz, I think. And so we could put in, let's just even see about 1 hertz if it can handle that. So there's 1 hertz right there. It's going through all its auto ranging pretty slow, and yeah, definitely makes it down there. Again, the ranging's not too good, so you could take it and go into manual. So it's definitely doing that. And 0.5 hertz they said it would handle. And it does look like it's working down at that level too. So pretty good range, 0.5 hertz to 5 megahertz. Here I've made a setup so we can kind of take a look at the frequency capabilities of the multimeter. And we just have a simple T here. We have a function generator set for pulse. And T is feeding the signal over the oscilloscope, and you can see the pulse right here. And it's of course periodic. And then of course with the T we're sending the signal also at the same time over to the multimeter. And it's supposed to be about 10 kilohertz, and you can see over here we're reading about 9.999 kilohertz. The secondary display is reading some microseconds up there, and want to take a closer look at that. But one thing you can do if you're just interested in the frequency, you can set it either for positive or negative edge triggered. It's by default set at negative edge triggered. If you just want to make it positive edge triggered, you simply press button number 4. And of course nothing's changed right there since it's periodic. And so one way we're triggering on the positive over here on the oscilloscope, the next one we're triggering on the negative. Okay, when we're measuring the frequency, we can also read the positive pulse width or the negative pulse width, which could be convenient. And I'll do some zooming in so you can kind of take a look at that. We have our 10 kilohertz signal here. Reciprocal, that's 100 microseconds. It's a periodic waveform, so there's one complete waveform that it repeats again. And I've made it asymmetrical here in the x-axis so that we're on for a certain period of time and then off, and we want to look at this positive pulse width right there. So the way we can do that, and I'll zoom in on it in a second for you, is I'll just take the B cursor and just slide it over so that you can see it someplace around in there. And I can read that directly out, and it's about 21.6 microseconds. And according to the meter, if you look at the top up there, it's reading that positive pulse width of 22.2 microseconds. So I think they're both pretty reasonable. Just bring that back. And so go ahead and zoom in on that. I'll stop the camera for a second. And here we have it kind of zoomed in on the oscilloscope, and you see there's that time right there, and it's 21.6 microseconds. And then what we could do is we could bring this over, and of course it will be just the difference between the 100 microseconds and that for the off time. But just so we can see that, I'll take the B cursor and just to kind of prove it, slide it over there. And then bring up the A, slide it over. And now we're reading, of course, the negative pulse width time period at about 80 microseconds. And again, this is a little bit crude, but just trying to show it as an example. So let's go back to the overall view of the test setup. So let's go ahead and see what the meter does. We'll take the negative. So now we're reading the pulse width of the negative portion of that pulse train, and it's 77.7 microseconds. And again, kind of crudely with the cursors, I got around 80 microseconds. So quite reasonable, I think. Okay, I've set it back to the positive, and it's 22.2 microseconds. Since it's 100 microseconds for the whole period, it's pretty simple. Just multiply that by 100, and you get the duty cycle. So basically, the on-time duty cycle, or the positive duty cycle, is 22.2%. And then when it's in its low state, it would be that 77.7 that was reading earlier. Okay, we looked at a positive and negative, the pulse width, but you can also do it directly with duty cycle. So if we press the button right here, you can see we get an enunciator of duty and a percent. There's our 22.22% for the positive duty cycle. If you need the negative duty cycle, simply press the button twice, and then you would get that 77.7%. The minus in front is to indicate that it's the negative duty cycle. This could be handy. I'm not an expert in motor controls and stuff, but I notice in some automation systems, a lot of times they're active low, so that they do their function when they're in the low state. Maybe this would activate a motor, and you're more interested in this negative one, that the motor's running 75% of the time if it's being pulsed or something. And then maybe some other thing, a lamp or something might be running on a positive and then or active high, and then you could check the positive duty cycle. So pretty convenient, getting the pulse widths, triggering it for your frequency, and also positive negative duty cycle. Measuring resistance, I've now set it under the resistance scale of the rotary switch. And in this one there are three functions. From the rotary switch you have ohms, continuity, and capacitance. And you can see the two soft touch buttons up here give you that choice. So they're showing you we're in ohms right now, and we can go to continuity with the beeper, or capacitance. The dual display, what you're getting up here in the 5,000 count display, is Siemens range, and there it shows microsiemens. And Siemens in the old days used to be called Mohs, and it's basically a measurement or unit of conductance, and so it's the reciprocal of resistance. So if you simply took this 10K resistance right here and took the reciprocal of it, you'd come up with 99.9495 microsiemens. I have a couple meters that measure microsiemens, kind of handy maybe in really high resistance measurements. This one here, I'm sure, it's a mathematical system. It's just taking the reciprocal for you if you want it. So something I probably wouldn't use. The value for this, according to the DMM Check Plus, it's supposed to be 9.999 k ohms. So 9 with 3 nines, and we're reading 10.004, and again we're bouncing around a little bit. You also have the rel button on this meter, so you could zero out the resistance of the leads, for example, or actually pretty much any offset value you'd like to have subtracted out of the measurement. And we'll be covering that a little bit more shortly. Capacitor, it's stamped on it, it's supposed to be 150 microfarads. And some of these meters can be really painful in finally getting the value, and this one is not too good. So if we clip it on there in the auto range mode, it takes pretty much, forever to come up with a value. So you could go have a cup of coffee or something, or write a book. And we're waiting. And there it comes up. It's supposed to be 151 microfarads. Again, that though was measured with an LCR meter, an AC signal. This is doing a DC charge discharge, so may not be too unreasonable. What the manual recommends is to minimize that really long wait period is possibly to select the appropriate scale. So if we took this thing off, kind of short it out for a second, and then take it out of auto mode, and then actually go to the 500 microfarad range. So there's 5 microfarad, 50, there's 500. Again, I'm looking over this side right here. Might be a little hard to read. Let's see if the speed improved any. So we'll clip it on there. And there it was about, what, less than 2 seconds. So probably not too bad. And auto ranging just takes it forever as it's cycling through its excitation signal and everything to come up with a value. But if you know roughly what the value is supposed to be and you set it to manual ranging, then it is pretty quick. Okay, let's move the rotary switch over to the diode measurement. Open circuit voltage of this meter is supposed to be greater than 3 volts, which is good. Some meters may have a little bit less voltage and maybe not sufficiently to turn on the junction of the device. So here we have a red LED and connected up just randomly so we can just check it both front to back. And so we're reading 1.6 volts, so looks pretty good for the forward voltage drop of a red LED. And then in the reverse direction, we get the OL, and we should still maintain an OL, so we're not getting leakages or anything like that. Putting it back on there just for a second, we can see in the forward bias if there's sufficient current to turn it on, and I think you can see it's definitely on, so it has enough to light up some of the LEDs. Here's a germanium. There's 3 of them here. I'll just grab onto one. Again, cathode with the band there, so we'll go right directly to it and measure the barrier voltage. It should be generally 0.2, 0.3 volts. And so it's 0.33 volts. So there we have germanium. Silicon, generally a half a volt, 0.7 and up. This is a 1N4007 rectifier diode, 1 amp one. Clip it on there. And this would be our silicon, and yeah, close to 0.6 volts, so 0.59. So silicon. And then again, you check your front to back to make sure that it's not leaking in the other direction. So you should be getting an AO over range overflow, and we do. So the diode testing here seems to be pretty good. And here we're checking the temperature probe, and I've been letting it go for a minute or so just to sort of stabilize, still drifting around a little bit. We're out in my garage. And according to my Fluke meter, it's supposed to be 56 degrees. This is reading 52.2 degrees Fahrenheit. The accuracy on this is plus or minus 5.4 degrees Fahrenheit, so it is within the accuracy. But it's a bit out. Most of my other temperature probes are a little bit closer. On the set button, you can press this and you can go from Fahrenheit to centigrade. So if you want to read it out in centigrade or Celsius, almost the two are the same, or you can go to the Fahrenheit. Okay, so showing the current ranges, we're still in the temperature mode, so I'm going to flip it over. Notice I have my leads in this position, not connected into the current input jack. So when I flip it over, I get an error and indicates that there's a bad fuse. Also, it could mean that the probes are in the wrong position. So if I take the lead out and put it over in the milliamp microamp port, you can see that that error goes away. If it still showed fuse in this port with these connected this way, that would be an indication that you have a blown fuse. Another thing is if you're over in the volts ranges, then it will tell you have a lead error, which is very good, meaning that you're thinking you're going to measure voltage, but you've got it in the current ranges. So if you notice, I go over here, we get a definite notice that we got a major problem there, that we have a lead connection. And then when you take it out and then put it back in, not a problem. So go back over to here and connect it into there. You can rail this out. There's a little bit of current. If you notice, that's microamps. So there you'd be hundreds of nanoamps, tens of nanoamps. And you can rail that out if that's a problem. And it's kind of neat. It tells you how much it's subtracting the particular value from. So we'll hook it up to the tester and measure that. So again, watching polarities, we're just doing the DC one. As you can see up here, it's saying DC. We'll turn it on. This is a higher value than the microamp. The microamp range is 500 microamps. So you can see we're in the manual mode and it's overranged on that. So we need to go take a look in the milliamp. And in milliamp range, we have 0.933 milliamps. And when we come back down to the microamp range on the auto mode, it gives us our highest resolution, and we have 0.9993. And according to the tester, DMM Check Plus, it's supposed to be 0.9999, so decimal and then 4 nines, so pretty close. Okay, switching over for AC, we'll turn it over to AC current, and then press the AC annunciator. And on the AC current, it's supposed to be 1.001. And again, it might bounce around a little bit, and we have 0.999. Also, again, remember, it also measures the frequency of the current, which is kind of nice. So we're reading the frequency up there of this current, AC current. Okay, what I'd like to show is the DC, AC capabilities of the meter. And so we're at 60 hertz, and we've got an amplitude of 1 volt RMS and a DC offset of 0 volts. And so again, at the 1 volt, we're reading 0.992 volts. So we can compute percent error on that. Okay, in this example, I've checked the AC-DC modes. So we have 60 hertz. We have an amplitude of 1 volt RMS for the sine wave. And we have a DC offset of 500 millivolts positive. So if we go back here, looking at the AC value that we're reading 0.95, and I checked with another meter, so it seems to be very, very close to being on. And we can also press the DC, and we should get our half a volt. And so there's our 0.5 volts DC. And then you can read the two together. You can get the AC plus DC, like some meters offer, which is kind of handy, which should be pretty close to about 1 volt. And it is. It's a 1.07. If you do the math on this, it comes out to be 1.07. And then one feature I really like about this is you notice now the enunciator's changed AC-DC without the plus sign. So if I press that, it splits the display, and it gives you the AC that you're putting in, the 0.95 volts, and it gives you the DC offset of 0.5. So say in an operational amplifier, stage, or transistor, or something like that, you could be reading an excitation test signal, the AC signal, up to maybe that 5 megahertz, and you can read the DC bias at that particular node. Now obviously you can do that by just simply flipping a switch on a normal meter between the AC and the DC, possibly, but this is really convenient to get it all in one display. And if you're checking a bunch of test points as you're troubleshooting, I think that could be a really nice utility convenience. So I really like that. Here I have the DMM connected up to a power supply through a little switch box. And we'll zoom in on the display so we can kind of look at some of the range button, for example, and some of the other button controls. Okay, in this mode you can see we're reading about 4.8 volts. We're on the 5 volt in auto ranging, so you can take it out of auto ranging. You simply just press this button and it's in the 5 volt. And each time you click it through, it goes through the different ranges and it tells you what they are. So there's 5 volt, it has a 50 volt range, and it seems to update pretty quickly. There's the 500 volt range, it has a 1000 volt range. And then when you come back, you're back to the 5 volt. And you do want to remember there is a millivolt range through the rotary selector switch. If you press and hold the button down, it will click back into auto ranging. Here we've been sitting at 11.5 volts for a few seconds. You can push this button, the secondary display gives you the minimum value. Press it again, you get the maximum value in the secondary display. And you can also get the average of those. And of course, since it's not moving right now, they're all showing up pretty much the same. Pressing and holding down the button will take it out of that particular mode. So to see an example of it operating, if I put it into the min-max and then turn the voltage up a little bit and then down a little bit, and then we can now take a look at that. Here's the minimum, here's the maximum, and here's the average. In this shot we're showing the 1 millisecond peak detection. And you can see right now I have it hooked up to a power supply and it's reading 7.58 volts. You can't see it's off the screen, but I'm turning the voltage down, nothing happens. If I turn it and exceed that peak value, you can see it updates. If I start turning the power supply back down again, as you can see it's holding that peak. And supposedly can capture it in about 1 millisecond. Obviously I'm not moving my hand that fast. You also have a minus button here. If you push this, it gives you the negative peak value. And since there's a positive supply, we don't have anything going on there. And you can hop back and forth between the two. Okay, let's take a closer look at the rel button. And this is actually, you can do a reference by what you're reading and then do subtractions for measurements after that. Or you can actually program in a reference. So you have two choices, which is kind of convenient. On this one, if you just press the rel button, it will take this value, place it in the secondary display, which is kind of nice. So it's telling you all subsequent measurements will have 10.13 volts subtracted, or the resistance or whatever. So again, for getting rid of lead resistances on low ohmic values, that can be nice and handy. So again, I'm off camera here, but if I turn up the voltage to about 12 or 13 volts, you can see we are now 2.48 volts above the 10 volts. Or if I go below that value, down around 8 volts or something, it's now telling us we're minus 1.9 volts below the 10. And we get a little triangle there for the delta symbol for the relative measurement. If you would like to program in a value here, which could, like I say, be convenient, you press the min-max button. It tells you a reference and you now can slide through that. So it was subtracting 10 volts, and maybe I want to subtract 9 volts or something from it. Use the arrow keys and you just simply move over to the digit you would like to do, and then you can use the plus and minus keys to increase it. So I'm going to go to 9 here because I want to subtract 9.13 volts, just arbitrarily chosen for example. Move over one more, and now I'm going to use the minus key, take it down to 0. And once you have it set, then you just simply press the exit button here, soft key 4, and it pops you right out. And now you can see I'm putting in some 8 volts into it, and I'm subtracting 9.13 volts from it, so my difference is 0.98 volts, again negative. If you leave the rail mode or you turn the meter off, your programmed reference is not saved, so that's one thing to remember. But again, kind of convenient when particular ranges you're working with. So I'll press that off, and of course it takes it right back out. And to show the example of the hold button, here I just press the hold. It gives you a hold indicator and then just simply freezes the display. If I flip the power supply off, disconnect it, you can see that it still maintains the display. Notice that the analog bar graph, though, is still active, so it's just freezing the numerical display at the top there. This meter also features an auto hold. Again, we had the hold there that we just demonstrated, but if I press it again, I get an A in front of there, and then I get a hold value up at the top once the display is stabilized. So, for example, then if I switched it off, and this thing is dropping down, it's holding that particular value. If you change it to some new value, you can see it takes several seconds for it to stabilize, and then it grabs it. So it's not a really touch hold. Could have some value to it, but not quite as nice as, for example, the flukes. This DMM also has 20 memory positions that you can store values into it. And the way that you would take a look at that is using this memory key, you simply just press it once, and you get a bunch of enunciators: store, recall, clear, and exit. And if you want to store this particular value in there, you just simply press the store key. And it will say the buffer 01 location, it's done. One thing I don't like is it takes it right out of it sometimes in some of the modes where maybe you'd want to scan through a few, but not a major problem. So let's say we want to store another one. I'll turn the voltage down a little bit. We'll just press store it into memory, press the store button. It's now in buffer location number 2, save, done, and it's out. And you can do up to 20 of these. If you want to then come back and recall, simply press the memory key and press recall, and notice it shows buffer 00 has nothing in it, but you can now move through those. So buffer 1 that we stored in is 12.29, and buffer 02 location is 8.99. And you can clear this by pressing it. It says, are you sure? Press it again, clear it, it's done. There's also an all clear capability, so you can clear all of them at once if you like. So kind of a handy feature. Again, you can store up to 20 of these. Also in the memory key, if you hold it down long enough, you have a backlight. So if we press this and hold it for about 2 seconds, it brings up a backlight. Again, kind of hard to see with the video because we have some noise and stuff in there. It has 6 yellow LEDs off the side on the green display. But I can say in person, it lights it up okay and not a problem. And as you can see, it also has an auto shut off. Also for AC signals, the meter supports DBM and DBV. And here you see I have set up a sine wave. Let's set it for 1,000 cycles. So there's 1 kilohertz. And let's set the amplitude for 10 dBm. And then what you can do is you can come over to this side, and you can see we do have a DBM key there. And I'm going to go ahead and zoom in on the screen again to kind of help it out. So here we have a close-up of it, and so we press the key to put it into DBM. And what it does is it continues to measure the voltage of the signal, and the secondary display gives you the DBM. And I tried it with a couple other meters, and they were reading 9.5 also, even though the generator was saying about 10, and we could check out and see if it's within tolerance or not. Another thing is you can set the impedance. It defaults to 600 ohms even if you turn it off, which is sort of a standard for audio. And the range on this is 40 hertz to about 20 kilohertz, again for audio. If you press the set key, you can actually cycle through and change it anywhere from 1 ohm to 1,990 ohms. So you just move through it. Right now you can see I've set it for 50 ohm because that's the load that I have on this particular generator. So that's kind of convenient. If you exit out of that, you also have a dB key right here, and if you press that, you get dBV. And it can be set also within a range of about from 0.1 volts to 5 volts. And dBV would be referenced to 1 volt. And again, you can do a set here, and as you see, it's referenced to 1 volt right here, and you can go through again with the arrow keys moving across and making your changes. So reasonably extensive system there, pretty handy. Okay, in this section of the video, I'll go ahead and take it apart. And it's one screw on the back. So you can turn it over here, and there's a screw located right at this point. And go ahead and open it. And I have to say, this is probably the hardest cover I've ever taken off of any piece of equipment. It was extremely painful. And in fact, I still can't quite get it open. You're supposed to take the screw like this, press in the back here so it cantilevers up, but there was just no way I could do it. The only way I can open it is pry bar it. I know there's some other people who have opened some of the less expensive models of this one on YouTube, and they didn't seem to have any trouble. I kind of looked at the plastics. It doesn't seem to be a major problem, but I just couldn't really get it open very easily. So I have to go in here and do quite a bit of prying. Okay, removing the cover. Again, there were 3 screws. They do go into metal inserts, which is a nice thing. And there are blast shields around the fuses. They also are long enough that they actually go inside the slots in here in the PC board. So give pretty good protection all the way around the fuses and the battery compartment. Here's a shot of the back of the cover, and there you can see the shielding that was put in place. And again, the large grooves, ribbing there that goes inside of the other piece when it's mated together. And there's some blast area pieces here, and these again are extended large enough to go down into the PC board. Okay, here I've kind of tilted the unit up a little bit so you can see it. And again, I'll zoom in this area and kind of talk about it for a few minutes, and then zoom in the upper areas here. In this lower portion of the meter, you can see here's the jacks coming in, and most of them are double soldered. This last one looks like it's just on one side. You have some high wattage resistors, slightly higher wattage than just normal surface mount. And here's your 10 amp current shunt for the amps. This is a 11 amp fast blow 1000 volt rated fuse. And over on this side is a 440 milliamp fast blow 1000 volt rated fuse. And that's, it looks like the shaft for the rotary selector on the other side. In this area we have a DF10, which is a bridge rectifier. It's 1 amp 1000 volt. Again, a high wattage resistor here for R1, PTC for over voltage protection, and there are some diodes sprinkled around. The spring over here, there is a metal backing on the case, and so this makes the electrical connection from the board to the case. This one appears kind of a little difficult. It's a resistor. It's called R7. When you kind of look down through it, it looks like it has a hybrid substrate in there, so probably maybe a precision resistor in that area. Some larger capacitors, and of course a lot of surface mount, a lot of transistors. In this area we have a chip up here. This is a Fortune semiconductor. It's the FS9704B, and it's a front-end DMM chip located right here. Over here we have analog devices. It's a true RMS converter. In this particular case, it's the AD636, the J, which is the 1% precision HZ converter. Over here we have a buzzer flanked by 2 crystals. There's a 4 megahertz crystal, there's a 4.1 megahertz crystal. And then this is a 8-bit microcontroller. It's the D78P0308 GC. I think NEC originally came out with this. This may be second sourced. Up at the top there are 2 infrared transmitter and receiver, it looks like. They are both populated. And that's for the intercommunication to the computer. Very deep grooves around the side here, again for protection when the case is enclosed there. And this large piece of plastic right here is actually set down inside and held captive. You can pull that out and a couple of screws you can remove the circuit board. Overall, layout looks pretty decent. Everything seems to be well soldered, you know, the surface mount and everything doesn't look bad. Okay, so I'll just kind of hold it by my hand and slowly go over it so you can get an idea of what it looks like. Another interesting thing is I don't notice any potentiometers, resistors, or variable capacitors on here. So maybe everything is calibrated through the microprocessor. And also, not sure why, but there's some ribbing on here and a little bit of air gaps. And if you see right here, it gives a little bit of flexing. And I'll have to wait till I see when I put the case back on, but that might be, makes it a little bit more softer for where you'd be gripping, because that's about where I'd be holding the case. If that's what they're doing, it's a pretty nice feature. The manual I got with my unit was just a small little print, and I found on the internet a PDF file, and I always like to print it in a bigger binder and then also add my own notes. And I would rate the manual overall, at least in this format, you blow it up, as pretty good. It's got a lot of ways of quick switch selection information, definitely gives you data on the different modes of operation. Even talks about DC and AC with a graph, and about the measuring the positive and negative duty cycle pulse widths. So overall, I think it's a pretty decent manual. One thing I did have is, and I'm going to have to postpone doing a software data acquisition, is all my computers, I have a couple and they're all 64-bit. When I put the disk in, it flags me that it can install, and please check if you have a 64 or 32-bit operating system. So I'll pursue it, maybe do a follow-up video on it. So what do I think of this particular unit? Again, it is a little bit expensive, especially if you're paying the retail of $293. Really love the dual display. I think that's a great feature. Accuracy of the meter seems to be pretty decent. The quality of the construction seems very good. The switch seems great, positive. And I do like DBM and DBV as a nice additional feature, plus seeing AC and DC at the same time. Having 20 memories for storage is pretty good. And of course you have the backlight that seems to work well. The auto hold is not the kind that I'd really prefer. I like the Fluke touch hold a little bit better. Overall feature set though is pretty impressive when you can alter the reference resistances or voltages in millivolt steps or 1 ohm steps, depending on which one you're activating. And going to 5 megahertz for the frequency is a nice thing. And the DBM's working from 40 hertz to 20 kilohertz. Negatives for me for the meter is I do kind of like the more gray silver back, and that's just an aesthetic thing because it still is clear enough to read, but it seems to be a little bit better brightness and contrast with the other type. And really don't like the beeping on, again, a minor thing, the beeping when you're changing ranges. I just don't see that as a utility at all when you get the tactile and acoustical feedback from the mechanical switch itself. Really dislike access here. This was a real pain in the neck to get this open. I still have to pry it open each time. And unfortunately that the software may only be 32-bit, even though I know you can sometimes install 32-bit on a 64-bit machine. I've got to pursue that and see what's going on with it. Another small negative is if you are on capacitance and you're in auto ranging, it can be very painful waiting for it to finally update it. But again, going into manual range and moving to at least the approximate predicted value you're going to measure makes it get the value much quicker. And again, sort of a personal thing, the test leads that it comes with I don't like much at all. Again, they're $10 accessories if you bought them separate, so they're not expensive, but was a little disappointed in their top of the line to have that kind of test leads given. Again, I like the flukes a lot better. And so overall, I would say the first half hour or so using it because of some of the annunciator things and fighting that access door and the probes, it was sort of a little bit of a negative. But now that I've used it for a couple weeks, I am starting to like it, and I sure think it's very feature rich. So I would give it a thumbs up.